Hi everyone, my name is Eric Lester. I graduated from Raleigh Charter back in 2015. For the last 4 years I've been up at Carnegie Mellon University in Pittsburgh studying physics and computer science. And today I'm going to talk a little bit about one of my favorite physics principles that is unfortunately a little bit too relevant to us in this day and age, and that is confinement. Quick note before we jump in, I'm going to be using the words confined and constrained pretty interchangeably throughout this video, so just be aware. Now, what do these words actually mean? Well, a dictionary definition for confinement may go something like this. It means something to the effect of the state of being restricted within certain limits. The physics definition isn't all that different. For example, we say that an electron is confined to an atom since it can't, under normal conditions at least, escape from the atom. Now, what's so wonderful about confinement is that to be such a simple principle, nature has a very peculiar way of dealing with it. Let's consider an electron, for example. An electron can have any energy at once. We can represent this as a spectrum, where the electron can take on any energy among an infinite range. Now let's ask the question, what happens when we confine the electron? Two very important things happen. Number one, the energy can no longer be zero. Number two, the energy must be a discrete, quantized value. Now we can arrive at these results by using the Heisenberg uncertainty relationship and the Schrödinger equation, but that's really not the point of this video. Instead, I want to qualitatively appreciate these results. Now I'm not going to argue that they're strange. There's nothing in the physical macroscopic world that looks anything like this. But I'm actually going to argue that these results are not quite as unintuitive as they might initially seem. Now to understand why, we're going to have to ask a much more general question. Here we were looking at what happens to the energy of an electron once it's confined. But let's ask the more general question. What happens to a problem once we constrain it? I'll offer an answer to this question in the form of an example. Let's say we're trying to solve a maze. Now there are an infinite number of paths that lead from the start of the maze to the end. Most of them just involve going in circles for a long time before eventually meandering to the exit. Now let's constrain this problem by requiring that we find our way from the start to the end of the maze in fewer than 50 steps. Now the number of solutions to the problem has drastically gone down. We've gone from an infinite number of solutions down to just a few. And in fact, the more we constrain this, the fewer solutions we'll have. Constraining a problem necessarily reduces the number of solutions, and as a result, it's an extremely powerful problem-solving tool. We all understand this intuitively, even if we aren't consciously aware of it. Think back to the last time that you did a jigsaw puzzle. How did you start it? Well, you probably started by doing the frame, or maybe there was a region of a particular color or with writing, something distinguishable that you could start with. You started by constraining the problem, looking for only edge pieces or only pieces that were red. Now, just because there are fewer solutions to a constrained problem does not mean that it's necessarily easier to solve. In fact, constrained problems often require the most creativity to solve. The hardest real-world problems are difficult because of their constraints. For example, how can I engineer a processor that costs less than the previous one while still being more energy efficient and more powerful? These are really hard questions. But interestingly enough, further constraining them can actually lead to creative solutions. It's just the natural way to solve a problem, as we've already seen. When you're faced with a real, vague, big problem, don't be afraid to constrain it, even if it feels like you're moving away from the solution that you should be going towards. Don't be afraid to look at a limiting case, or a smaller problem instance, or tweak some parameters to make the problem a little bit different. More constrained problems give more creative solutions, and oftentimes the constrained problem offers enough information to solve the general case as well. For example, if you remember at the start of this video, we were discussing the case of an electron trapped in a box. And now here we are, addressing something much more general than that. By investigating what was seemingly a completely disparate case, we were able to understand something much more general about a problem that we weren't even asking about. A small physics problem ended up teaching us something fundamental about problem solving as a whole. And that's an extremely important takeaway. Even the smallest, most constrained problem offers us great insight into something more general. Thank you for watching, and I hope you enjoyed it.